Thank you very much for the introduction. And first and foremost, I would like to say thank you to the organizers, the organizer of the workshop and the organizer of the overall program for putting together the event and for inviting me. It's a great pleasure to be here in Bonn at HIM. So, as the title suggests, as the two previous talks that we had this morning and some of yesterday, I will talk about micromagnetics, but the focus will be a bit different because I'm a numerical analyst. So my work is to design and to analyze numerical schemes, and this is what I'm going to present today. Let's start. So this is the plan of the presentation. After a brief introduction to motivate the work, I will present the model in which I'm interested, and then discuss numerical schemes. I will consider both the static setting, which will be essentially an energy minimization problem, and the dynamic setting, which will be the approximation of the right equation of motion. But for the second one, I will give just a sketch, and I will finish the talk with some concluding remarks. Okay, so let's start. I will start with a very easy slide. So everybody should be familiar with that, maybe even from school. So classification of magnetic materials. So materials can be classified depending on their magnetic behavior. And I will maybe forget about the last two classes and focus on the three, which in which the magnetic moments somehow experience some collective behavior. And then we all know that you can have, say, ferromagnets in which neighboring magnetic moments want to be parallel to each other. Then you have, so, antiferromagnet. This is the picture somehow in which neighboring spins would like to be anti-parallel to each other, and they are equal to each other. And then, the net magnetization is, say, 0 in the ideal case. And then you have a third type, so ferrimagnet, like this one, in which, like antiferromagnets, neighboring spins want to be anti-parallel to each other, but they are not equal, so you have some net magnetization. Okay? And to my understanding, most of the work has been dedicated to the first class, even in mathematics. But recently, so there is a renewed interest in also two other classes of magnetic materials, so antiferromagnet and ferrimagnets, because somehow theoretical and experimental studies seem to suggest that they are very good candidates for the spintronic devices of the future. So, in particular, to improve some of the functionality of spintronic devices based on ferromagnet, because of some interesting properties, such as small or zero, even in some situation, in the ideal case, magnetostatic interaction, which allows somehow to put close to each other different magnetic elements without so avoiding that they interfere to each other, for instance, or ultra-fast dynamics, so things happen on a faster time scale, and at the same time they still experience or exhibit features like domain wall and skyrmions, like in ferromagnets, but they move faster again. So in view of applications, this is nice. For this reason, somehow there is interest in somehow deriving maybe continuum models in the spirit of micromagnetics, also for these classes of materials. And of course, there is the need of reliable numerical schemes to perform numerical simulations, because maybe you can do atomistic simulations, but then this will put a strong restriction on the size of the somehow sample that you can simulate because of the limit posed by the computational resources that you have. Okay, and this will be the focus of my talk, essentially. As far as I know, there are, on the physical market, there are two main models to describe antiferromagnet, two continuum models, I think, to describe antiferromagnet. And in this talk I will focus on one of them, which I will call, say, a two sublattice model, for obvious reasons that you will see in the next slide. So the reason is that somehow the order parameter, so the quantity of interest, so the quantity which describes the magnetic state of your material, is actually made of two unit length vector fields here, M1 and M2, so defined on the domain under consideration and attaining value onto the unit sphere here. And the energy functional we restrict to exchange interactions takes this form here, and for material coefficients which satisfy somehow inequalities such that the gradient dependent contributions are positive definite here. So this is the energy functional, and you see three contributions which have a name. So the first one is usually referred to as inhomogeneous intralattice exchange interaction, and models nothing but, say, the standard Heisenberg exchange interaction for each of the two subfields. The two other guys here somehow on the other end involve the interaction between the two fields. Okay, that's why they are called interlattice here. And the first one models somehow the interaction between neighboring spins of different type, while the second one it's a local interaction between the two fields. Okay, and then from these two you can gain information about the net magnetization of the sample by summing the two fields together. It's not clear to me, at least I could not find it, where this model was proposed for the first time. I just found a very simple derivation of it, of this energy functional, in this paper here, when the idea is really you start from, so at least you start from the Heisenberg, so the atomistic form of the Heisenberg energy, and then somehow with nearest neighbor interaction between spins, and then somehow you divide this sum into three terms depending on the fact that the spins are of the same type or different type, and by performing some limit, some Taylor argument, then you end up with the three terms. Okay, so heuristically this is how it works. Okay, so this is the energy functional in which I'm interested. Now I would like to pose the static problem, and this is very standard, so I just define the space in which I'm looking for minimizer, so the set of admissible pairs, which is this one. So both fields, we would like that both fields are H1 and are sphere valued almost everywhere. And then we consider just a constant minimization problem. Okay, so we want to minimize our energy functional in this set here. Okay, then what you can do is like you do in micromagnetism or for harmonic maps and so on, what you can do is to derive, say, the Euler-Lagrange equation associated with the minimization problem, and you end up with this, these two equations here, so a system of two equations, where somehow the two ingredients appearing here, so the effective field and this space here, are somehow the effective field that you usually have in micromagnetism, but here now somehow the L effective field, you have to take the Gateau derivative with respect to the ML field. And in particular, you will notice immediately that besides the standard exchange term, for the two terms involving somehow, for the two coupling terms, you will have somehow the other field appearing in the effective field. Okay, so this system, or this will be a coupled system of equations here. And this term, this space here, is the space of pointwise orthogonal vector fields, which naturally appear when you are dealing with somehow unit length vector fields, and like in the harmonic map setting, for instance, you can write this in strong form, and then you get exactly the very same Brown equations that you get, say, for standard ferromagnet in micromagnetism. The only difference is that you have two somehow, but say formally they look the same. So this is the standard, and this is the somehow the equation satisfied by stationary points of the energy. We want you, maybe you are interested also in dynamics, and then you're looking for somehow, so your two fields M1 and M2 will depend also on time, and then, so the equation that has been proposed is again, so it is well known that the well-established model to model the dynamics of the magnetization is the Landau-Lifshitz-Gilbert equation, and you have also this, you have it also here, and formally it looks the same, you see, but again the difference is that the effective field now will depend on both fields, so they will be coupled via the expression of the effective field. Eta L and alpha L are dimensionless parameters, with alpha L having the meaning of damping. Okay, so this is the system, and all properties, by construction somehow, all properties that you have for, say, the standard energy equation, the structure is the same, the property will be the same. So you have a constant preserved dynamics here, and it is a dissipative dynamics, where somehow dissipation is modulated by the parameters appearing here, and you have the usual interpretation of the two terms on the right hand side that are precession, the first one, the conservative one, and damping, the second one, the dissipative one. Okay, so far so good. One final comment. For simplicity, for ease of presentation, I restricted myself to the exchange only situation, but of course if you want to see interesting things you have to include more. So if you want to see more than constant fields in some simple situations, so you want to include other terms, and we can do that, we can analyze them. For instance, so the interaction with an applied external field will look something like that, where you have the total magnetization here, so F plays the role of an applied field, and the interaction is of this form. You can consider the magnetostatic energy, and again, so the input, somehow this is the stray field operator, so the solution of the magnetostatic Maxwell's equation, and the input somehow is the total magnetization again. And you can consider also other terms like anisotropy and the Diallo-Shinsky-Mori interaction. And these usually, so by physicists, are added to the model separately. So if phi here is, say, the anisotropy function incorporating information about the easy axis of the material, usually they consider separately the two, so one for M1 and one for M2. And similarly for the Diallo-Shinsky-Mori interaction, so D here is say the spiralization tensor, which for instance for bulk DMI is just the identity up to a constant. So, but the main message here is that somehow, so the Brown equation and the energy equation are coupled, but only exchange coupled. Okay, so all these contributions, so for linearity or by construction, somehow do not contribute to the coupling of the two equations. So coupling will happen only through the exchange energy contribution that I have presented. And actually, that is why I included it in the presentation. So it's the only one that I will consider throughout the presentation. Okay? Okay, so far so good. Let's talk about numerical methods now. And somehow, what are the challenges? Actually, yeah, this slide, it's the same slide that I would use talking about, say, micromagnetics for ferromagnets. So these are essentially the same challenges, so it's a nonlinear problem. You have the non-convex point-wise unit length constraint that you want to realize at the discrete level. When you want to do analysis, so the energy equation can experience non-uniqueness, positive blow-up in time, and low regularity. I'm not claiming those results for the coupled system, but I would imagine that the situation does not become better, so I would imagine that this will occur, this will happen as well. Then you have the energy law that you want to preserve also at the discrete level, and in addition, maybe you have somehow the fact that you are dealing with a coupled system, so this should be done efficiently in order to make your simulation feasible. And the aim of my work here is, as I said at the very beginning, to design and analyze structure preserving numerical schemes, in which by structure preserving I mean exactly that I want these things to hold also at the discrete level, and if they do not hold, I want to understand some of the error that I make here. Okay? So let's start. I will present the ingredients, so the common ingredients of all the schemes that we consider. So for simplicity, for the time discretization, I will just consider, say, a uniform partition of my time interval or of my, say, time horizon, and I will denote by tau the time step size here. Okay? Constant for simplicity. For the spatial discretization, I want to use finite elements, so I will consider in 3D a tetrahedral mesh, a conforming mesh of my domain, and I will denote by h the mesh size, so the maximum diameter of your elements of your mesh. So these are some of the two parameters that go to 0 when you want to analyze convergence of your scheme. Okay? And the basic space in which I'm looking, which I will somehow, so I will approximate my two fields M1, M2 using first order finite elements. So VH will denote the space of vector valued, so three-dimensional, but each component is a piecewise linear and globally continuous functions. Okay? So first order finite elements. So before I introduced two guys, X, which was the set in which I was looking for minimizers, for instance, and somehow K, which was the space of orthogonal vector fields. And here I introduced somehow two discrete counterparts of them. So X, H, delta, so you see an additional parameter delta here, and somehow these are the pairs such that each field is a finite element function here, and you see that somehow the constraint, the unit length constraint, is introduced in this way. So on the one hand, I impose it only at the vertices of the mesh, which is also a natural thing because these are the degrees of freedom. Okay, so this is a first somehow relaxation. The second one is that I relax it, so I don't require here inequality, but I admit an inequality, so this is a larger than or equal to 1. So somehow I'm violating it, but I introduce some control of it, so some control of the violation, which is somehow controlled by this parameter delta here appearing here, and the control is in this sense here. So IH here denotes the interpolation. Okay, so you just consider your nodal value and consider the piecewise affine interpolation of them. Okay, so this is XH delta, and the other guy was the space of orthogonal vector fields. Here we consider a discrete version of it, but as we did before, again we impose the orthogonality that we want to impose analogously, but only again at the vertices of the mesh. Okay, so this is a linear space, and this is the one that we will consider. So these are the ingredients of the method. Basically what I'm doing here is to extend, to adapt methods that are known for ferromagnet to this setting here. And yeah, two important references as, for instance, this work by Alouche for the Landau-Lifshitz-Gilbert equation in micromagnetics, or this work by Søren Bartels for harmonic maps. Okay? Let's start. And I will consider algorithms for the static problem, so for computing minimizers. And my approach will be essentially to set up a gradient flow, and which will somehow induce an energy decrease in dynamics, and then to approximate it with a time-stepping method, so that I will get an iterative algorithm. And so I will consider somehow an Hilbert space H with inner product here, such that so my set of admissible pairs is continuously embedded in H on the one end, and then so somehow this is the second inequality here, and the first one that I want is this one. So this is the L2 norm, and this is the H1 norm. Essentially, I will think of something between or as L2 gradient flow or H1 gradient flow. Okay, morally. And yeah, as I said, this is the H gradient flow of the energy, so two equations, one of each, of them. And as I said, I will obtain an iterative algorithm from a time-stepping discretization of this equation, where the spatial discretization will be based on finite elements. Okay? And somehow, I'm not claiming that I can be able to compute minimizers with this approach, but somehow I'm claiming that I'm able to compute stationary points with low energy, because somehow the energy will be decreased, so I can hope to get something that possibly is a minimizer. Okay? The first algorithm, okay, let me go through it. So algorithm 1, I call it coupled discrete flow for one reason that you will understand immediately. So let me go through the lines. So the discretization parameters are, okay, the mesh size h, the time step size tau, which we have already seen. Here tau is a fictitious time step size because the time has been introduced artificially by us in the gradient flow approach, and then there's some tolerance here. What we do is the following. So we start from an initial guess here, so I will first guess for a minimizer, and then in the loop we do the following. So we iterate 2 steps until a stopping criterion is met. And the 2 steps are this one, okay? So first of all, we compute an update V1 and V2 in the discrete tangent space, so each guy is orthogonal in the sense, in node-wise, to the guy that from which you start, from the current state, such that this variational formulation posed in the discrete tangent space is satisfied. And then, once we get our update here, we somehow perform the first order time stepping here to get the next one, okay? And let's have a look at this equation somehow compared to this one, okay? You see, so this is the time derivative, which is essentially this term here. Oh, sorry. Okay. This is the term involving the energy, which is the right-hand side here. Just think of the expression of the energy. But they have 3 additional terms on the right-hand side, which arise from an implicit treatment of these energy contributions, and note that I'm not using the same somehow implicit methods for the 3 contribution. So for the Heisenberg exchange, say, I'm using an implicit Euler approach, because, so this guy has a sign, it is dissipative, so I want dissipation here, because I want to compute minimizers. For these 2 other guys, which do not have a sign, I use, say, a Crank-Nichols method, so the midpoint rule, because this is symplectic method, so in the energy, this will not contribute somehow to the energy law. We will see that in the next slide. And in particular, so this could somehow make the energy a bit higher, possibly, okay? And so I'm iterating these 2 steps until a certain stopping criterion, namely this one, is met, okay? So which somehow, the meaning here is that when the update is small, very small, you stop it, because somehow you are numerically converged, okay? And the output then, so when I met the stopping criteria, I just define the last guy as my approximation of the stationary point, okay? So this is the algorithm, and so just to a comment on the projection update, you see that there is no normalization of my magnetization. So even if I start from the sphere, this is a 2-dimensional sketch, then I compute my perpendicular update, but the next one will be, so the first one already will be out of the unit sphere. And if you proceed, things get worse and worse in general, okay? But I will show you that we can control this error, okay? These are somehow the numerical analysis of the scheme, the results that you can prove on the method. If tau, maybe I forgot an important comment here, sorry about that. Because of these 3 terms, this will be a coupled system, okay? I don't have 2 separate equations, one for, say, M1 and one of M2, but I have a big system because of these 3 terms, okay? This is important. Okay, so these are the results of the numerical analysis. If the time size is sufficiently small, each somehow variational problem is well defined. Again, under this assumption, the stopping criteria will be met in a finite number of iterations, so I will converge numerically, to something. This is the discrete energy law, and here you see what I was mentioning before. Somehow, all these are somehow the new energy minus the old energy, and this is equal, so you have equality here, to something that is non-positive. So somehow the sequence of energies generated by the algorithm will be monotonically decreasing, which is somehow a good property if you want to minimize the energy. And this will happen unconditionally, so without any restriction on the discretization parameters by construction. And then the two final estimates tells us that we have, if tau is sufficiently small, we have stability, so somehow everything is bounded by the, more or less, the energy of the initial condition here. And we can control the error in the unit length constraint that I was mentioning by this equality here. So here we have essentially the H1 norm of the initial conditions, of the initial gas, and we have tau, and the constant C here is independent of all discretization parameters. So when tau goes to 0, the error, so this guy will converge to 1, and then somehow this is exactly the constraint that I want to satisfy. Okay, fine, this is the result. You see algorithm 1, there is a number because there is another one. Okay, so algorithm 2. And here it is. I will be quicker here because it has the very same structure. Actually, it coincides with the previous one, apart from one aspect, which is this one here. You see something missing here. Okay. Essentially, what I'm doing here is different from what I was doing before. So for the, say, Heisenberg exchange interaction, I still use my implicit Euler approach, my dissipative implicit Euler approach. But for the other two guys, the one which are involving the two fields, so incorporating the interaction of the two fields, I will consider an explicit Euler approach, so I don't have them on the left-hand side. And this, on the one hand, will spoil a little bit the energy law of the method, but the advantage will be that this is not a coupled system of two equations. Here I have one equation, and then I have the second equation independent of each other. So in principle, I can solve them in parallel. And so rather than a big linear system, I have to solve two smaller linear systems of half size. Okay? So this is the difference. The rest is the very same as before. Okay?
So I'm a bit confused why it looks a bit asymmetric in the sense that A11, so that is if L is equal to 2, or while you have kind of a general L on the left-hand side and A11 on the right-hand side and no A22?
Because it's a mistake. This is ALL. Thank you. Thank you for pointing this out. Yes, sure. And maybe it was also here, or maybe that was. Yes. Yeah, sure. This is a typo. So here you have somehow the L field, the L constant that you have. Yeah. So this should be ALL here. Thank you. Yes, okay, so this is the algorithm, and this is somehow the counterpart of the previous proposition about well-posedness and stability of the numerical scheme. And here now you see that well-posedness is unconditional. So before I needed to assume that the time step tau had to be a bit sufficiently small because you don't have somehow the coupling terms which have the bad sign in general. This is the interpretation of it. The rest is the same, excluding the discrete energy law that now you see have some additional, is spoiled by two additional contributions. But again, you get the energy decreasing property if tau is sufficiently small, because these are higher orders. So you see a tau squared here. So if you tau is sufficiently small, you can somehow incorporate these two into these two, and you get what you want, energy dissipation. Nice, so we have two algorithms, and for both of them, we can prove the following convergence result. So if the initial gas is uniformly bounded independently of the discretization parameters, which is essentially not an assumption because you can choose them as you like, so you can make them independent of everything, then, so assuming that somehow tau and epsilon go to 0 as h goes to 0, just to have only one discretization parameter, but unconditionally, that what we can prove is that somehow, what we can prove is this convergence result So upon extraction of a subsequence, so the sequence of approximate stationary points will converge towards a stationary point of the energy. Okay, this is the result, and okay, so we have two algorithms somehow. So we would like to compare them to each other. Okay, because if we have two, so the question is natural. Which one would you like to sell somehow? And in this table, somehow I'm summarizing the properties of the previous proposition, and you see that basically many of the properties coincide. The difference is that the coupled algorithm, so the first one, somehow has a well-defined iteration only if tau is sufficiently small, but it is unconditionally energy decreasing, whereas for the other one it's the other way around. So it is unconditionally well posed, but it is energy decreasing if tau is sufficiently small. And the other difference is this one, highlighted in red, is that I have to solve one 4n by 4n system, where n here is the number of vertices, y is number, so I have n, the number of vertices, I have my finite element functions, which are vector valued, so 3n, I have two of them, so 6n, but I have two constraints for the orthogonality, so minus n, so I end up with 4n, and here is somehow the overall number of unknowns is the same, but I have two 2n by 2n systems, so this is the difference. And I want to point out that all thresholds involved here, so when I say sufficiently small, depends in this way from the coefficient of the L2 term of the energy. Okay, so this is a kind of theoretical comparison of the scheme. Now I would like to do some numerical comparisons of the scheme. I consider really a toy problem here, so a toy example, not some fancy micromagnetic simulation, but I make the energy slightly more interesting, incorporating also an external field here, which I will treat explicitly. Okay, essentially the same results that we had before will apply also to this energy. The problem is posed on the unit cube. I choose these values for the material coefficients, and I will choose somehow an applied external field constant and somehow aligned with the x direction. Okay? These are for completeness the discretization parameters, but you can forget about them. I just want to mention that somehow the parameter, the discretization parameters and the material constants are chosen in such a way to resemble somehow the right size that you should consider in micromagnetic simulations to resolve the dynamics, to resolve the length scale and everything. Okay? What I will do will be to somehow evaluate two different choices of this coefficient here to understand the meaning of this guy. So different values of A0, then I will discuss two different values of the initial guess, and then of course I will compare to each other the algorithm, so algorithm 1 and algorithm 2, and two possible choices for the gradient flow metric. Let's start with the first one, which is a kind of sanity check, essentially. So I want to consider A0, A0 here equal to 100 and minus 100. And then from this, you see that somehow this term will either require the two fields to be parallel to each other or anti-parallel. So if A0 is negative, then you get, say, an antiferromagnet behavior, whereas if A is positive, you will get somehow a ferromagnetic alignment. Okay? So for antiferromagnet and ferrimagnet, A0 in general will be negative. Okay? It is a kind of sanity check. And here I use initial condition essentially aligned with the field, in the sense that it is 100 up to some numerical perturbation to make things a bit more numerically, say, stable. And we get what we expect, actually. So if somehow A0 is equal to 100, so in particular positive, then the stationary point is perfectly aligned with the field. And if A0 is negative, we get somehow this thing. And as I said, you would like that M1 and M2 are somehow anti-parallel to each other, okay? And you see that this almost happens, at least for the second and the third component, but you have a first component which is there because of the field. Okay, so here are the picture to understand. On the left you see the case of A not positive. You see only some vector field because they are perfectly superimposed. Okay, here, so this is just constant, the x-axis here. And here you see what I was mentioning before. You see somehow a kind of almost anti-parallel behavior, but a bit deflected in this way towards the applied external field. Okay, there is one question.
Same boundary condition in both cases, or no?
It's Neumann boundary conditions, so it's no flux boundary conditions here, as usually have in micromagnetism. I'm not imposing anything in the boundary.
So why this is perpendicular kind of to...
So I have to say that the fact, so somehow you expect this behavior because what I was saying before, but this degree of freedom is totally random and will depend on the initial condition. Because there is nothing which somehow select a specific direction here. So somehow maybe you would like to be anti-parallel. Because of the field, you have a kind of non-zero first component for both fields, but up to rotation you could get anything, and I got this particular orientation because of the initial condition that I chose.
But the initial condition is not the same in both cases.
In both cases it is the same. It is almost aligned with the external field. And you see that here nothing happens essentially, so it stays that. And here you have this, so they open until they reach this.
So it's some component this way and...
The field points in this way. Okay, so to me it was a kind of good, good result in terms of functionality of the algorithm. Okay, this is what I would expect. Say, the second experiment. So here I would like to compare the two algorithms. So algorithm 1, the coupled one, and algorithm 2, the decoupled one. And for both, I will consider an L2 metric and an H1 metric in the gradient flow. And just to summarize, so somehow, of course, so the L2, so let's compare, say, L2 metric for both algorithm and H1 metric for both algorithm, they converge towards the same thing, essentially, which is fine, but the limit that you have in H1 and L2 is different, and this is not surprising because somehow it's a different dynamic equation, so you cannot expect to converge towards the same stationary point. So this is fine, and you have different finite energies. Okay, the number of iterations, so you have significantly less iterations for the L2 gradient flow compared to H1 gradient flow for both algorithms. The average solve time, again, I compare them for both algorithms, and you see that the one of the decoupled algorithm is more or less than half of the one of the coupled algorithm. So somehow decoupling the equation is good for from the perspective of numerical linear algebra. So this is something that you want to do in principle, and I reported somehow the error in the unit length constraint. So the one that I can control with my analysis, and the infinity norm that should be 1, say, and you see that there is an error, but at least for this choice of tau, it's fine. Okay. So from this outcome, so this is not a general conclusion, but from this experiment, I would say that you would like to use an L2 gradient flow with the decoupled algorithm, because this is faster and the error is fine. Okay, so the less iterations and the quicker iteration. So I would go for this one based on the outcome of this experiment. Okay, there is
quick question. So you have vastly different number of iterations, but the solve times are comparable. Per step, is this time per step or?
So you see that somehow, if you focus on one algorithm, say you have much less iterations for the L2 gradient flow, but more or less the same solve time. Okay, so using a metric,
How is it possible? You're iterating more, but you takes the
I
same.
think so. There is the motivation goes in the stopping criterion, okay? Because in the stopping criterion, the metric enters, okay? And if you consider H1, you want to make it's a larger guy that you want to make smaller. So it takes more, and you need more iteration.
But then your steps, individual steps on the right, are much faster.
This will depend on the metric, but rather on the type of algorithm. So the metric, because somehow on the left-hand side of your system, you still have the stiffness matrix and the mass matrix.
No, but a single iteration.
The single iteration is faster for the decoupled algorithm,
In H1.
and it's not affected by L2 and H1 metric.
But how come you have the same time, average solve time,
Between what?
between H1 and L2?
Yeah, because actually you have both at the stiffness metric. It's not
Iteration,
surprising
you
to
have
me.
more iterations.
More iterations because of the stopping criterion.
Yeah, but if you have more iterations, you run longer.
Yes.
So how
That's why I was saying I want to consider the L2 gradient flow. Because it's fast.
how come the times are not different?
Now this is the average solve time for one step.
Okay, so for one iteration.
Okay, I forgot this important information. Maybe.
Yes.
This is for one iteration. Okay, so the total time is essentially the product of these two numbers. Okay, sorry for the misunderstanding. Okay, so, I would like to go for this one, but then, actually maybe you don't, if you consider a different initial guess, namely made by a random initial condition, when in each point you just consider a random unit vector, and then you see that somehow all conclusions that I was mentioning before are the same, but look at the error in the unit length constraint. For the L2 gradient flow, the final approximation has length equal to 2, which is twice what it should have. Okay? Whereas for the H1 gradient flow, you have 1. This is also somehow explainable by the theory, because in the unit length, in the L1 estimate of this error, so in this estimate here, somehow on the right hand side you have the metric, and so this is understandable, but you see that for the H1 gradient flow, things are much better here. I have to say that such a random initial condition, it's not something that you encounter. So, I mean, usually you have some reasonable guess, okay? And if you're really without a guess, then you start from this one, but then you should consider an H1 gradient flow, because it behaves better. Okay, so this is what I wanted to say about the stationary case, and a very, very brief sketch now about the dynamic problem. So we had our coupled system of 2 LLG. What we will do is somehow to exploit what we did for the stationary case. And then what we do is that first we reformulate the equation in this form by applying vector identity properties. And second one is I define V as the time derivative of the magnetization for each of the two fields. And then I obtain this form here, and from this, then I define my algorithm, and the message here is that it looks very similar to what we had before, because somehow the Landau-Lifshitz-Gilbert equation is nothing but, say, an L2 gradient flow plus the conservative term. So basically, we consider the same algorithm here. Here I'm comparing somehow the terms here, and somehow if you exclude the red term, you will have somehow what you had before with the decoupled algorithm. And I would like, so here I cannot choose the metric, because the metric is imposed by the dynamic equation, it's L2, but I can choose somehow the treatment of the fatty field contributions, and I think the good option here is to go for the decoupled algorithm, because it is significantly faster. And I don't want to start with a random initial condition here, but I usually don't do that when I do micromagnetic simulation. And okay, I'm not saying anything about the results, but most of the results transfer clearly. And I'm actually, this is still work in progress. I think so. I'm working on the proof of convergence of the approximation generated by this algorithm towards a weak solution of the LHG equation, of this coupled system of LHG equation. Okay? This is essentially what I wanted to say. So, some conclusion. I presented this model, this two-lattice model for antiferromagnet and ferrimagnetic materials. I described numerical algorithms for them, for both the static case and the dynamic one, focusing on the first one, which is a kind of a preparation for the second one, actually. And for these algorithms, we can prove well Posner stability and convergence results. What I'm doing now, besides, I'm planning to say more so conclude the theory, first of all, and doing more maybe physically meaningful numerical experiments. What I'm also doing is, what I would like to do is to compare this numerically and analytically, this model with the second model that I was mentioning in the very beginning for anti and ferrimagnetic material, which uses a different order parameter, which is a so-called Néel vector, which can be understood more or less as the difference between M1 and M2, and the resulting dynamics is inertial dynamics. So you have your LHG type equation plus some inertial terms, so it's a second time derivative. And then we would be interested in understanding the connection between the two models. All right, this is what I wanted to say. One last slide, maybe some advertisement. Together with former colleagues from Vienna, I'm co-organizing the next edition of HMM, so the International Symposium on Hysteresis Modeling and Micromagnetics. This will take place at the beginning of June in Vienna at TU Wien. So the abstract submission will open next week. So we will have keynote speakers, contributed talks, and poster presentations. So I strongly invite you to take a look at the web page. Maybe I will send you some spam email to some of you in the near future. Apologies in advance for that. But please come. This is an interdisciplinary forum focused on hysteresis and micromagnetics for mathematicians, physicists, engineers, material scientists, and so on. And should have taken place in 2021. It didn't for obvious reasons, but it will take place now in June. So please come to Vienna in 6 months. This is what I wanted to say. This is the virtual paper that will appear in hopefully 1 month or so. Many thanks for your attention.